Catalysis and colloids. From this presentation onwards, we will be studying in detail catalysis and colloids. What is catalyst? A catalyst is a substance that increases the rate of a reaction by providing an alternate path of lower activation energy. Since catalysts are not consumed in a reaction, very small quantities of catalyst are required to enhance a reaction rate. So in this reaction profile diagram, you can see the catalyzed reaction has higher activation energy, whereas a catalyst decreases the activation energy and hence provides an alternate pathway for the completion of the reaction. Now there are some substances as well that enhance the activity of a catalyst. They are known as promoters. And those substances which decrease the activity of a catalyst are known as poisons. The catalyst possesses many characteristics like it remains unchanged in mass and in chemical composition at the end of the reaction. Very small amount of catalyst is generally required. The function of a catalyst is only to alter the speed, but it can never initiate a reaction. The catalysts are generally specific in their actions, and finely divided catalysts are more effective in heterogeneous catalysis. Now the catalysis can be broadly divided into two groups, that is homogeneous and heterogeneous catalysis. So in homogeneous catalysis, when the reactants and the catalysts are in the same base, that is either they are liquid or gas, the process is said to be homogeneous catalysis. In this, they must either all gases or soluble in proper solvents. For example, we can see the process of hydrolysis of an ester or oxidation of SO2 to SO3 in lead chamber process where catalysts are H positive and NO respectively. Coming towards heterogeneous catalysis, the catalytic process in which the reactants and the catalysts are in different phase is known as heterogeneous catalysis. This is also known as surface catalysis because in such catalysis, the reaction occurs at the surface of the catalyst. Coming to its examples, they are ammonia synthesis and methanol synthesis where catalysts are iron with aluminium oxide or zinc oxide and chromium trioxide respectively. Here in this, one of the reactants may be in liquid and the other in gaseous state, while the catalyst can be in solid state as well. Next is adsorption theory of heterogeneous catalysis. The modern adsorption theory is the combination of intermediate compound formation theory and the old adsorption theory. The mechanism involves the 5-step. First is the diffusion of the reactants to the surface of the catalyst. Adsorption of the reactant molecules on the surface of the catalyst. Formation of an intermediate. An intermediate is formed on the catalyst's surface. Then desorption of the reaction products, and then those products they get diffused away from the catalyst surface. The surface of the catalyst, unlike the inner part of the bulk, it has free valencies which provide actually the seat for chemical forces of attraction. For example, when a gas comes in contact with such surface, its molecules are held up there due to loose chemical combinations. If different molecules are adsorbed side by side, they may react with each other, resulting in the formation of new molecules. And the formed molecules may evaporate, leaving the surface for the fresh reactant molecules. And this theory explains why a catalyst remains unchanged in mass and chemical composition at the end of the reaction and is effective. You can also see this video regarding the adsorption theory. Here on the platinum surface, the hydrogen molecules and the ethene molecules, they are coming in contact. They are actually diffusing to the surface of the catalyst and are finally getting adsorbed. Now there is an intermediate formation between them. Now they are desorbing from the surface of the catalyst and they are diffusing away from the catalyst surface. Do catalysts live forever? No, they can as well as die. They can die from poisons which contaminate the catalyst or large molecules which can cover the catalyst. They can also die from overheating, overpressurizing, crumbling or crushing. Next article is shape selective catalysis by zeolites. The catalytic reaction that depends upon the pore structure of the catalyst and the size of the reactant and the product molecules is called as shape selective catalysis. So here zeolites are used. Zeolites are good shape selective catalysts because of their honeycomb-like structure. They are microporous aluminosilicates with the general formula as given, and the metal can be either sodium, potassium, calcium, where Z is also the number of moles of water of hydration, which can highly be variable. There is a three-dimensional network of silicates in which some silicon atoms are actually replaced by aluminium atoms to produce aluminium, oxygen and silicon framework. So because of this three-dimensional cage-like structure, zeolites can be used as ion exchange materials and selective adsorbents. They act as molecular sieves for the reactants, and to achieve this, when they are heated, their water of hydration is lost. And once the water is removed, the zeolite structure becomes porous and the pore size is generally of the range 260 to 740 pm. Now the size of the porous cavities, it always influences the catalytic activity of the catalyst. Zeolites are widely used as catalysts in petrochemical industries for cracking of hydrocarbons and isomerization. A very important example of zeolite is ZSM5, which converts alcohols directly into gasoline by dehydrating them. So here is again a video which will show you the action of zeolites.
Structure of zeolites. Zeolites are mica porous aluminosilicates having the general formula MXN AlO2X SiO2 MH2O. In zeolites, aluminium atoms replace few silicon atoms in three-dimensional network of silicon dioxide. The overall structure known as aluminosilicates acquires a negative charge. Cations such as Na+, K+, or Ca2+ balance the negative charge. These have open structure of aluminosilicate frameworks, which enables them to take up loosely bound water or other small molecules in their structures. The negative charge of the aluminosilicate framework is neutralized by exchangeable carbonations of valence N. Zeolites have high porosity due to the presence of one, two, or three-dimensional network of interchannels and cavities of molecular dimensions. These give them honeycomb-like structure. Zeolites are used as molecular sieves and can separate molecules of different sizes and thus important industrial applications.
So, depending on the size of the reactants and product molecules relative to the sizes of the cavities of zeolites, as you have seen, the reactions occur in a very specific manner. For example, alcohols, as already told, they are converted into gasoline, that is petrol, using a zeolite catalyst ZSM5, and 5 is for their molecular porosity. The alcohol is dehydrated in the cavities by the protons, and this results in gasoline. So here again there is a video to show cracking long chain hydrocarbons, how this is done, where alcohols are converted to gasoline. Next is enzyme catalysis. So similar type of catalysis processes also occur in our body, where the chemical reactions occurring in our body are catalyzed by enzymes. Enzymes are actually protein molecules of higher molecular masses and form colloidal solutions in water. Now there are numerous reactions occurring in the body of animals and plants to maintain the life processes, which are catalyzed by enzymes. So here is a list of few enzymes like invertase, zyamase, diastase, maltase, urease, pepsin, their sources and their enzymatic reaction, means on which substrate molecules they react. Example, invertase, it acts on sucrose to convert it into glucose and fructose. Similarly, zyamase converts glucose into ethyl alcohol and carbon dioxide. So enzymes are highly effective catalysts and they catalyze a number of biochemical reactions. So they are also termed as biochemical catalysts, and the phenomena is known as biochemical catalysis.
Is it odd to have a favorite protein? Well, I don't think so. Probably because my favorite protein happens to remind me of one of my favorite childhood games, Pac-Man. If you haven't played Pac-Man before, then chances are we're much older than you. But now you can play it on Google. Just Google Pac-Man. It's a Google Doodle. Anyway, I digress. But see, in Pac-Man, you have this little character. It goes around, finds these pebbles, and the pebbles fit right into it. Well, a lot of illustrations that you will find of enzymes, they happen to look, at least us, a lot like Pac-Man. I remember P for Pac-Man and P for protein. Most enzymes are proteins. Now, in the game, we mentioned there are these little pebbles that Pac-Man goes after. Well, enzymes have a specifically shaped area called an active site, where items can bind. The items are called substrates. It's very specific binding because the active site is specifically shaped for the substrate that binds there. Very specific. So what happens when a substrate binds an enzyme? Well, usually the substrate is held there with some weak bonds because it's not going to stay there forever. And something called induced fit will happen, which means The active site can change its shape even more to bind that substrate, like an enzyme substrate hug. The enzyme can either build up or break down the substrates that specifically bind to it, and we call the resulting item the product. An enzyme has the ability to really speed up reactions. Reactions that technically could happen on their own, but with the help of enzymes, they can be sped up to make processes effective for life. Let me give you a great real-life example. The enzyme lactase. Another really cool thing about enzymes is that they often end in ASE, like lactase. Many sugars, on the other hand, end in OSE, and lactose is an example of a sugar. Lactose is a disaccharide, meaning it contains two sugar molecules bound together. We don't actually digest it so well in that form. It's big. The enzyme lactase has the ability to break lactose down into smaller parts that our body can digest. And this is a lot better option than waiting for a chemical reaction with lactose to happen spontaneously. Now, with the lactase enzyme, lactose can be broken down quickly and digested. Now, there are some people that do not produce enough lactase. They can be what we call lactose intolerant, which means that if they consume foods that have lactose, such as milk, it can make them sick. They can't break the lactose down efficiently without lactase. In that example, one thing to point out, lactase, the enzyme, can break down a lot of lactose, the substrate. The lactase doesn't get used up in the reaction. It's still there. We call enzymes a catalyst because they can be used over and over and over and over in the reaction. By the way, your digestive system uses all kinds of enzymes. You have lipase, and that breaks down lipids, which are fats. You have amylase, which breaks down starch. You have protease, which breaks down proteins. So, as you can see, the digestive system is very involved with enzymes. Another thing to point out is that enzymes don't always work alone. Sometimes they get some help. Some often underappreciated but essential little helpers are called cofactors and coenzymes. They may bind to the substrate or to the active site. They help the enzyme do its job of building up or breaking down substrates into products. Now, you didn't forget our Pac-Man analogy yet, right? In the game Pac-Man, there are these ghosts, and when they touch the Pac-Man, it makes this sound. It's like... no, 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 no. And the Pac-Man shape gets all distorted in the process. So what does this have to do with enzymes? No, there aren't ghosts around, but enzymes do have certain ideal conditions that they like. For example, an enzyme that is in your stomach would have an ideal pH that is very acidic because the environment in your stomach is very acidic. Different enzymes have different ideal pH and temperature ranges. If an environment changes out of an enzyme's ideal pH or temperature range, then something that reminds me a lot of that horrible sound I tried to make can happen. The enzyme becomes denatured. That means its shape becomes distorted. It can no longer bind to its substrate. It can no longer work correctly. It is finished. Well, that's a dramatic end to enzymes. Keep in mind that if you have an interest in this topic, many medical researchers have a large focus on enzymes. Enzymes regulate a lot of the body processes, and many diseases can involve specific enzyme production, or the lack of it. Well, that's it for the Amoeba Sisters, and we remind you to stay curious.
So from the video also you have clearly studied the mechanism of enzyme catalysis. So first is binding of the enzyme to substrate to form an activated complex. Then that activated complex decomposes to form the enzyme back and the product. Characteristics of enzyme catalysis. So enzymes are highly efficient, they are highly specific in nature, highly active under optimum temperature conditions, highly active under optimum pH, and increased activity can be done in the presence of co-activators and coenzymes. So there are many metal ions that act as coenzymes in our body to enhance the activity of an enzyme. And next is the influence of inhibitors and poison. So all these things, they can affect the working of an enzyme in our body.